Hi, in this video we're going to introduce the concept of momentum, and this will cover two of the learning outcomes that we have shown as A and B. So it's used the principle of conservation of momentum and appropriate relationships to solve problems involving momentum. Also knowledge of energy interactions involving the total kinetic energy of systems undergoing various types of collisions. Momentum is defined as the product of mass times velocity. And momentum has the letter P. And so momentum, product of mass and velocity, would just simply mass times velocity. Has a unit just which is the combination of mass and velocity, so kilogram meters per second. And momentum is a vector quantity. So therefore it'll have magnitude in kilogram meters per second, and it will also have a direction. Now in higher we're going to be studying momentum, linear momentum, so that's momentum only in one plane. And quite simply, for example, we could have an object that has a mass, let's say it's 3 kilograms, and if it's moving at 5 meters per second, its momentum P would be times V, 3 times 5, and that would be 15 kilogram meters per second with a direction to the right. Now usually when we're talking about momentum, we rarely treat things like this in isolation, and what we're mainly interested in is collisions, and what happens is two objects interact with each other. And so let me give you a few examples of what I mean by a collision. And so as I'm sure you can imagine, that you have two objects traveling towards each other. They each have their individual masses and velocities, and what we're really interested in is to be able to quantify what happens if we know the masses and the velocities of each of these. We want to try and quantify what happens to these objects post collision. And that's where we come on to the law of conservation of linear momentum. So the law of conservation of momentum, as you can see here, states that the total momentum before a collision or an explosion, which is we're going to treat as just another type of a collision. So the total momentum before a collision is the same as the total momentum after a collision in the absence of external forces. Now this is something that you are asked quite regularly. You're asked to state what the law of conservation of momentum is. And the easiest way to state it is that momentum before a collision is equal to momentum after a collision. And one of the biggest mistakes that you can make is forgetting this last bit here. So in the absence of external forces, it wouldn't be marked correct unless you include this last bit. And so one of the biggest mistakes you make is you say the momentum before is the same as momentum afterwards, but you must include in the absence of external forces. So aside from the law, what we have is we have a collision. And so let's just say, for example, that you have one object that's traveling like this, you have one object that's traveling in the opposite direction, and they're obviously going to collide. And so this would be a before, and then we can have an after. Let's just say, for example, that during the collision somehow they manage to stick together and they move off in that direction. And so how we apply the law of conservation of momentum to a problem like this is that we'll create a formula using mv, using the momentum. So we look at the momentum of this object, and so we have momentum And what I'm going to do is, because this is the initial velocity of this object, I'm going to call it mu. And I'm going to add that to the initial velocity of this, mu. I'm going to give the objects names. I'm going to say that this is object 1 and this is object 2. And so I'm going to have the mass of object 1 times the initial velocity of object 1 plus the mass of object 2 times the initial velocity of object 2. And the law of conservation of momentum says that that together must equal the total momentum afterwards. And so I'm just going to say mv. And I'm going to say 1, 2, because that tells me that they're joined together. And so I have now created a formula which I can use. If I know what the mass is of it and I know both velocities, I'll know the mass afterwards because that's the combined mass, and I can then work out a velocity after. Because there isn't a set formula for this, you're going to have to do that every single time. And there is an awful lot of scenarios which you could have. So the scenario we've looked at is that you have two objects moving towards each other. After the collision, they stick together and then move off in this direction. We could have the two objects that are moving towards each other stick together, move off in the opposite direction. You could have two objects moving towards each other. They can then rebound off of each other. We could have two objects that are moving together and they don't stick together, but they move off in the same direction, and you could have exactly the same where they move off in the opposite direction. There are many different scenarios of which you can have a collision. So you can have a faster moving object colliding into a slower moving object, both moving into the same, off in the same direction, and again any number of combinations of this. And so what you have to do is you have to read the question, and from reading the question you then have to come up with a formula of what the momentum before and the momentum afterwards is. What I would recommend, and I'm a big fan of this, as you'll know, is drawing a diagram. So you read the question's in words, try and get rid of the words as quick as you can and make it into a diagram, make it into a sort of pictorial thing. Each of these things, we're going to have an M and a V. And so, for example, something like this. So let's say the momentum before is going to be mu. So m1 u1, m2 u2, and afterwards we're going to have mv and mv, and they're going to equal each other. So for this scenario, our formula will be that. Now, because momentum is a vector and velocity is a vector, you must be really super careful with your signing convention here. In this case, the velocity is positive. In this case, the velocity will be negative. We'll always generally treat left to right as being positive. And so here we have a positive velocity, a negative velocity. And here we'll have negative velocity and then positive velocity. And what you'll find, we'll do some examples of this, that you'll find that as long as we include the correct signs for our velocities when we're trying to find an unknown velocity, so say we're trying to find the final velocity of this, then as long as we're true with our signing convention, that'll come out as, in this case, as being a positive velocity. If we were looking for this one, the number would come out as being negative. You'll get to see when we actually do some practice calculations. So that'll be our first thing. Let's do a couple of worked examples to see how we do this in practice. We'll start with something really simple. So we have a 60 kilogram mass moving at 5 meters per second to the right, and a 40 kilogram mass moving at 3 meters per second to the left. They collide, there's a collision, and they stick together, and the velocity is doing something. Now, I know common sense is going to say this one will have the greater momentum, and if they stick together, then I know that the velocity is going to be going this way. But we don't really need to worry about which direction it is, because our answer will come out. If we're treating everything from going left to right as being positive, if we get a negative velocity at the end, we know that that's moving from right to left. But you'll see. So from this, we have our simplified diagram anyway, which is the question, and so then we just need to come up with our formula. So we'll have mu plus mu, and that's going to equal mv. So this is mass of 1, mass and velocity of 2, and then this is the combined mass afterwards, which you can call it 1, 2, 1, 2. Okay, put in the numbers. So we'll have 60 times 5 plus 40. Now, must remember, crucial here, it's moving from right to left, and so that must be -3, so -3. And then that's going to equal 100, which is the combined mass, 60 and 40, V12. Work out what these are. So we're going to have 300. Now this is going to be -120, and that will all equal 100, V12. This side is going to be left at 180, equal to 100, V12. So V12 will be 180 divided by 100, and that will give me 1.8 meters per second. So the combined velocity of this is 1.8 meters per second, and we must say to the right. Done. So another example. So we have two objects, again moving towards each other, as you can see. Now, after the collision, object 1 starts moving off from right to left at 7 meters per second. Find the velocity of this object after the collision. Again, the process is exactly the same. We'll have mu plus mu, and that's going to equal mv plus mv. Again, we'll put the numbers 1, 1, 2, 2, 1, 1, 2, 2. Substitute the numbers in. So we have 5 times 15 plus 10 times from right to left, so -30. And then that's going to equal 5 times -7 plus 10 V2. Simplify. This is -225 equals -35 plus 10 V2. Now you can cut out a few steps here. I mean, you don't need to do this. Taking that over to the other side, this is going to turn positive. So we're going to have -225 plus 35, which is going to leave us with, so 10 V2 is going to be 190, -190. And then so V2 is going to then be -19 meters per second. Now, because we've got the minus, this kind of signifies our direction anyway. Sorry, this signifies our direction. So what we can say is it's 19 meters per second to the left. Okay, and that's our final answer. Now, this is me making up examples on the fly, and obviously we can see that if that's moving at 19 meters per second, that way it wouldn't work. But you see the process of how you would do that calculation. Okay, moving on. There are three types of collision that we can have. I know I went through earlier when I said there's numerous different variations of a collision, but this is something different. There's three specific types of collisions. Now we'll have elastic collisions, and elastic collisions don't really generally tend to happen very often, other than when they specifically design a question to make it an elastic collision. Now, with an elastic collision, momentum is conserved, and then EK, kinetic energy, is conserved. Okay, so kinetic energy is conserved as well as momentum. Momentum is always conserved. In inelastic collisions, momentum is conserved. EK is not, so EK is lost. If you find that your EK is gaining, you've done something wrong. We don't ever have a scenario where we get energy in the collision, where we gain energy in the collision. So with an inelastic collision, kinetic energy is always lost. And finally, we talk about explosions, and where P is conserved. And in this case, there is no EK before and there is lots of EK afterwards, but what we have is EP is converted to EK. So we'll look at some examples and we'll find out how to determine what type of collision we have. So an example might be that two snooker balls, both have the same mass on a snooker table, are travelling towards each other and have a direct hit, both travelling at 1 meters per second. After the collision, one of the balls moves back the way it came at 1 meters per second, and find the velocity of the second ball after the collision. So again, what we're going to do, MU, MV, MV. Now, 100 grams, we're going to have 0.1 times 1 plus 0.1 times minus 1, and then that's going to have 0.1 times minus 1 plus 0.1 times V, in this case 2. I'm sure you can see what's going to happen here with the momentum. The momentum before 0.1 plus, and then we're going to have minus 0.1, and then minus 0.1 plus 0.1 V2. So this is going to equal 0.1 minus 0.1, which can be 0, equals minus 0.1 plus 0.1 V2. V2 is going to end up, take this over to the side, it's going to become positive. So we'll have positive 0.1 divided by 0.1 of velocity thereafter will just be 1 meters per second, and that's going to be to the right. Okay. Now, to determine whether this is an elastic or an inelastic collision, we need to work out the kinetic energies of all objects involved in the collision. So I'm just going to separate my page into a before and after. And I'm going to work out EK1, so EK half mv squared. So that's a half times 0.1 times 1 squared. And that's going to be 0.05 joules. And then EK of the second object, half mv squared. Now, energy is a scalar quantity, therefore direction is irrelevant. The fact that that's -1 here doesn't mean that it's going to be -1 here. Just ignore the minuses with energy. And so again, we're going to have 0.1 times 1 squared. That's going to be 0.05 joules. The total energy, EK total before, is going to be 0.1 joules. Then we'll go through and we'll work out the total kinetic energy after. So EK is equal to mv squared. We're going to have, so again, for this, it's -1, we're going to ignore the minus, just have half times 0.1 times 1 squared, just going to go 0.05 joules. EK of the second bit, EK, so it can be again 0.05, and then the EK total, (0.1 joules). So kinetic energy before is the same as kinetic energy after. Energy is therefore it is an elastic collision. So for our next example, we'll stick with the snooker balls, and so all of them will have a mass of 100 grams. Now what we have is first ball coming at 1 meter per second, striking a ball at 2 meters per second, traveling in the opposite direction. After the collision, ball 2 stops, and V2 is going to do something. So as before, we have our diagram mu is equal to mv. Put in our numbers, 0.1 times 1 plus 0.1 times -2. And that's going to equal 0.1 V1 plus 0. So work out what this is. We're going to have 0.1 minus 0.2 is equal to 0.1 V. We're then going to have minus 0.1. Therefore V1 is going to equal minus 1 meter per second. So this is minus 1 meter per second, or 1 meters per second to the left. Alrighty. Now let's work out the kinetic energy. So EK before I'll just combine it all in one. Half times 0.1 times 1 squared plus a half times 0.1 times 2 squared. And that's going to give me 0.5 plus, so we're going to have 4, 0.2. So my total energy before is going to be 0.25 joules. EK after EK is equal to half mv squared plus half mv squared, and then now we've got a half times 0.1 times 1 plus 0. If the velocity of this is 0, then EK is going to be 0, and that's just going to work out as 0.05 joules. So here you can see the energy after is less than the energy before. We can then say EK is lost, therefore collision is inelastic. And so there's an example of a elastic collision and an example of an inelastic collision. The very, very great majority of collisions, nearly all of them are inelastic. With whatever happens, you're invariably going to lose kinetic energy during the collision. Now, explosions. We can treat explosions in exactly the same way as we would a normal momentum calculation. So, for example, where we have, let's just think, if we have let's have a gun, and it's going to fire a bullet. And so the bullet is inside the gun right now. If the mass gun is equal to 4 kilograms and the mass of bullet is, say, 10 grams. Okay. Now, what's going to happen is before firing the gun, the momentum of the gun and the bullet is 0. We can have M for gun, V for gun, for U, that's U, and then M bullet, U bullet, And then after, when we fire the gun's going to recoil. So we're going to have M gun, V gun, plus bullet, V bullet. We know that in an explosion it's a special case of momentum calculation. We know that because before the explosion the velocity of that is going to be 0, therefore the momentum of that is going to be 0, and the momentum of the bullet is going to be 0. The momentum before an explosion is always going to be equal to 0. And so what we can say is that the mass of gun times velocity of gun plus mass of bullet times velocity of bullet will always equal 0. So the combined momentum after the explosion is always going to be 0. And if you take that over to the other side, that the mass of gun, velocity of gun is going to equal mass bullet, velocity bullet. So we're going to have the combined momentum of the gun is going to equal the combined momentum of the, well, not the combined momentum, the momentum of the bullet, but they will act in opposite directions. Okay, so be aware. Although I'm taking this over, I'm not going to include the negative because that one goes that direction, that one goes that direction. And so if the gun recoils at, let's just say 1 meters per second, then we can just simply find out how fast the bullet's going to go. And so we've got mass of gun, which is 4 times 1, which is equal to then 0.01 V bullet. V bullet. It's going to be 400 meters per second. Okay, and that's how you do explosions. So to sum up what we've done, we're looking at momentum. We've defined momentum as being P, and that's mass times velocity. It's a vector quantity, and the unit is kilogram meters per second. You can calculate momentum individually for an object, but more often than not, we're going to use momentum calculations when objects are colliding with each other. In this case, you're going to sketch a diagram, you're going to come up with a formula which will suit the scenario, and then you can calculate the missing single value that you don't have. You can have 3 types of calculation. We can have inelastic collisions where momentum is conserved but kinetic energy is lost. Elastic collisions where both momentum and kinetic energy are conserved. Explosions, momentum is conserved, but EP is converted into EK, and we've got that special way that we can do it. So after this, if you go through the course notes, you'll see a number of worked examples and going through inelastic collisions, elastic collisions, and an explosion. And after that, there's worked examples for you to do yourselves. All right, thanks for watching. Bye now.